Okay, all right, great. So yeah, anyway, welcome back. So yeah, today we'll continue talking about the different thread categories or thread models for quantum computing systems, and kind of where we, as a reminder, where we left off and the plan for today. So we talked about fault injection in NISQ quantum computers, and then the three remaining things we'll cover up today is side channels in NISQ, mainly about information leakage at the different gate operations in the QPU or the controller levels. And we'll talk about fault injection in FTQC and then side channels in FTQC, which are quite similar to the NISQ, but because you have now the decoder error correction codes, there's some sort of new parts. So for the first part, I think we can talk about the side channels for NISQ. So here's the different side channel threads in NISQ. And similar to fault injection, kind of want to ask, like, for side channels, why would somebody want to attempt a side channel to leak some information? So some motivations for an attacker to leak information, for example, could be leak the input or the output data. So if you have some sensitive data that you're working on, the input itself might be valuable, like a medical record, or the output, which is the results of the computation. And then so far, we don't have any quantum memories or quantum random access memories. So all the input data and all the output data is just classical. So there's nothing that prevents you from cloning this data, although you cannot clone the actual qubits as you're doing the computation. And then also for the side channels, it might not be just the data, but maybe the sequence of instructions or gates that you're executing. So a lot of people are trying to develop new algorithms, or they have some intellectual property in the code that they're executing. So stealing a sequence of instructions or stealing basically the gates or the algorithm that's executing would be a type of a confidentiality breach with respect to the intellectual property. And then also sort of at the higher level, there are things like, for example, timing and different patterns. So maybe you can learn some information from when somebody's executing some code, like, for example, or how often they're using the quantum computer. Let's say, before holidays, UPS runs more optimization because they have more packages to route. So by analyzing some timing patterns or just learning about the timing of the operations or the quantum computation itself, you might leak some interesting information. So this is all kind of just some motivations for why we worry about side channels. And in classical computers, there are many examples of different side channels. In some of the future lectures, when we talk about some lessons from classical computers, I'll mention these in detail. But one interesting thing is that the side channels are not just from the execution of the instructions, but also from things like operation of the caches or contention on some buses like PCIe or network. So there are many different ways where you can have the side channels, and that's why I'm going to categorize this for NISQ quantum computers as well. And similar to the fault injection, we'll focus on the controller and the QPU as sort of the two main parts. So in the next few slides, I try to kind of define a few different categories regarding the side channel and kind of different things we want to look at. So the first one is sort of the type of the leakage, or otherwise like a physical observation. So this is what are you the observable signal, or what are you trying to observe? And here there are many things. It could be timing, power, electromagnetic, acoustic, optical, or thermal. So these are sort of the main types of side channels that have been demonstrated in classical computers, and they could be applied to quantum computing systems as well. So let's say the type of leakage is sort of here at the bottom of this picture, and we'll build up different layers as we talk. And yeah, I think they're mostly self-explanatory. The categories, timing is basically that how long it takes to execute something. It could be, execution of, timing of one instruction. Maybe, for example, on different quantum computers, different gates might have slightly different timing. So you could maybe learn the type of quantum computer you're using by measuring the timing of the gate, or maybe the timing of the whole algorithm. But the timing could also be like in the controller. So like when the controller is doing maybe some error correction, maybe some timing differences can reveal information. So the timing can be anything from like one instruction to the operation of the whole thing, or even like I mentioned in the beginning, like what time of day you're running something. Like, for example, uh, in the quantum computer, you observe that no circuit is executed at midnight, and you can guess from that that the quantum computer is being calibrated at midnight, and that actually can leak some information. Power also probably self-explanatory. You basically measure the power consumption. Um, this could be either of the QPU or the controller. Perhaps in the QPU, maybe the power consumption is dominated by the cooling, which maybe hides some power consumption of the actual gates as they execute. You can have EM, um, RF, or other kind of electromagnetic waves from the controller, or from the cables that are connecting the quantum computer. Acoustic is pretty usually pretty low bandwidth, but it's kind of interesting. For example, some examples from classical computers. People have looked at like the speed of the CPU fan, so you can sort of from the sound you can guess how fast the CPU fan is rotating, and then from that you can guess how much computation the system is doing. Even cooler from classical one, people basically have observed that as you charge and discharge capacitors, you can actually hear a little bit of like a click, like a very small click. So by monitoring the sounds of the capacitors, for example, in the motherboard, you can figure out some things about the operation of the computer from the sounds that they generate. So there's some, timing and power, let's say maybe more straightforward, maybe higher bandwidth, and some things like acoustic or thermal would be kind of more weird things, maybe lower bandwidth, but still very interesting. So like thermal, also it's actually pretty low bandwidth, but again, from the way the chips heat up or cool down, you can guess some things about the operation. So these are all sort of like different types of things that you can observe that would be sources of information leakage. And I mentioned bandwidth already. So when we talk about side channels, one metric that's often used is bandwidth. Is basically how much information or bits you can get through the channel per unit time. And then this very much depends not just on like the type of channel, but also what what access the attacker has, maybe different analysis techniques that I'll mention on next slide. So it's not just that purely the type of leakage, also kind of how you measure it, what equipment you're using. But very roughly, you have things like, at least in classical computers, things like thermal channels, which is probably like around, like 1 bit per second. So thermal channels are very slow. It really depends on like the material properties, how fast things heat up and cool down. And yeah, maybe you can get like 1 bit per second of information, which is super slow, but maybe it's enough to leak like a cryptographic key. Acoustic would be faster, power, EM, optical, into hundreds of kilobits per second. Timing, probably the fastest channels are, at least in classical computers, are like cache timing channels, which is about like maybe 1 megabit, maybe more than 1 megabit per second. So you go from like 1 bit per second on the thermal side to like cache-based channels, and which would be like 10 megabits, quite fast. So the range of the bandwidth is really huge, and we don't have yet good idea for quantum computers, but you can imagine there will be kind of similar things, that maybe thermal channels would be much slower than some EM or optical or some timing channels. Um, um, so now the next layer in our picture is sort of the leakage source, or where in the system stack, or where basically in the system does the leakage occur. And then the leakage sources can include either the application, API if you're talking to the cloud, some OS kernel, microarchitecture, circuit, or the physical layer. So you would have the different sources, and then different sources, and then these are the types of leakage. And again, application is sort of like due to the operation of the application high level. This actually could be either sort of really the quantum circuit that's executing on the system, or maybe you could count the code that's running on the controller as the application. API cloud would not be very specific to quantum, except that if you want to learn about, for example, like timing of when the circuits are executed, so like scheduling some information about how the operations are running. Currently there's no there's no OS or kernel for the quantum computer itself, but maybe for the controller, on the controller there could be some operating system that manages it. So that could be a source of leakage. Microarchitecture, so different modules within, for example, digital to analog converter would be one module within the controller that could be contributing to the leakage. And then, at the very lower level, you have actually the circuits, and then the physical layer. So these are all different sources of the side channel leakage. Now, another thing to consider is sort of, are there any shared resources? So, what, if any, resources are being shared? And you can think about sharing within the QPU, within the controller, or within the cloud. So, of course, within the cloud, there's a lot of sharing because many users are using the cloud. But then within the controller or the QPU, at least currently, there will be much less sharing. So the different side channels could be, through, in the microarchitecture through some shared resources, or if, there's no sharing there, you can still kind of measure, for example, execution of the application, even if there's no sharing. And then I think maybe two important notes. So the sharing can be either temporal or spatial. So, in any cloud-based system, you're temporally sharing. So, one user is running, then you have another, so that would be temporal sharing. And spatial sharing basically means multiple users running at the same time. And when we have spatial sharing, it almost certainly implies multi-tenancy, that multiple users are running concurrently on the same machine, which is not supported by the quantum computers today, but could be in the future. So this kind of an interesting, there might be, like, for example, from the research side, there might be some interesting side channels when you have some spatial sharing, but spatial sharing is not enabled in practice. So you kind of have to, depending whether you assume there's multi-tenancy or not, you could have different types of side channels. So these are kind of the shared resources. Within the QPU, currently there's really no, the QPU is just basically the qubits and the couplings. There's nothing really to be shared unless you have multiple users running on the QPU, which again today is not supported yet. Within the controller, there's many more options for sharing, because, for example, the controller has to store information about the control pulses, like for different qubits, different control pulses. Maybe it has some memory for storing the programs that are being executed through the controller. So, even if you have some temporal sharing, if different users run on the same quantum computer at different time, some information like the gates that they executed might be stored in some memory. And then so some memory within the controller could be like a shared resource that, if I'm just making up an example, like, if somehow the controller is able to execute a quantum gate, more quickly, maybe it means that the information about that quantum gate was already in the memory of the controller because another user used the same gate. So some sharing of some memory or caches within the controller could be a source of side channels. And then API cloud. Again, nothing really quantum specific, but if you're sort of trying to reverse engineer the way the quantum computer cloud operates, or maybe try to guess how many users they have, or try to guess how they're scheduling different users, then by observing when you submit a job, when the results come back, things like that, it could leak you some information. So I think the API cloud would if there's a shared resource, which usually there is, it will be mostly, for example, like timing. But for the others, there could be possibly some other sources as well. Next one that's interesting, also important, is sort of the access level, which sort of the amount of access that the attacker has to the system. So basically there's either local or remote. So there's sort of local means that you are with the machine or on the machine. So like local physical means that I can touch the machine, measure something, some power, some properties of the machine. Local software would sort of mean that maybe I'm not physically at the machine, but I can upload some code and run it. So if you're able to upload some code um, and run it, then that's sort of like a local software access. And then remote basically means that you're only interacting with the system through the network. So if we consider like a cloud-based quantum computers, remote would be basically anybody connecting to the machine, and then local would be in this case, some malicious users in the data center, or sorry, some malicious, operators in the data center that can connect um, to the machine. So you can have the uh, local access, or you can have remote access. So like um, for local access, then you can basically, for example, measure directly all the kind of really all the properties if you have um, local access. But if you have remote access, for example, it would be very hard to measure temperature unless there's like a thermal sensor that you can access through the network interface. So some of these things become sort of very difficult or impractical when there is only remote access. Um, um, yeah, so these are sort of the main levels. And I wanted to add some comments about supply chain, since it sort of relates to to amount of access you have. So again, so supply chain attacks basically means that somebody is able to modify either the software or the hardware of the component of the computer as it's being manufactured or deployed. So usually when we have like a different attacks, um, if the supply chain is not mentioned, then that we assume that everything is correct and the attacker is either remote or local. But if we consider supply chain, it's sort of like could be like a type of like a local attack. So if through the supply chain I'm able to modify and put some component into the computer, then effectively I'm on the machine. So I gain some local access to the machine. So that's sort of some overlap between local and supply chain attacks. And then another part that's sort of important is sort of either software supply chain or hardware supply chain. So um, um, again, I guess somehow lately there's a lot of in the news about software supply chain, like Python packages and things like that being compromised, and exactly the same thing can apply to quantum computers. So from a quantum computer perspective, there could be a software supply chain issue with the quantum circuit. So, for example, you're doing a project for this class and you download some quantum computing library that you're not familiar with, and maybe that has some malicious instructions in it. So that would be like a software supply chain issue with the quantum circuits. But also on the quantum computer side, you can have software supply chain issues where the controller is running some software, and then maybe that software has been compromised. Or of course on the hardware, if somebody can change the hardware of the controller or the QPU, then that can modify its operation. So I think regarding the side channels and the supply chain, software supply chain, of course, hardware supply chain attacks in the controller. I think having hardware supply chains in the QPU itself would of course be really bad, because you can change the operation of the QPU, but I think it might be more difficult to leverage that for a side channel, for example. So I think it mainly focusing on the controller part. Um, and then last but not least is kind of okay. So what with all of this, what are we trying to leak? And then coming back to the first slide, we can either be leaking code or data. So so the target assets is things that you want to get out, and then so it could be some information about the code. It could be either you're trying to learn the full code, or maybe just a type of program that you're executing. So, is it a optimization problem versus a quantum chemistry problem, or maybe the algorithm that's being used, but you don't know the parameters of the algorithm. So when we think about leaking the code, uh, it's not kind of binary. Either I get all the instructions or nothing. It could be just maybe I want to guess, is there quantum Fourier transform subroutine within that piece of code? So learning any information about part of the code or all of the code might be useful. And then for data, I think I already mentioned, input or output data, um, or ideally some intermediate data would be interesting to leak, but we cannot clone qubits, so we really cannot um, copy the qubits in the middle of the computation. You might be able to get the classical data that's coming in, or the classical output that's coming out, but things in the middle would be kind of hard, um, unless there are some special measurement techniques people come up with, or unless maybe you insert a measurement on purpose um, into the quantum circuit, but then it will be um, no longer a purely sort of passive side channel attack. Um, so maybe good point. Are there any questions about this different categorizations? Um, you know, in the end, sort of, for each attack can sort of go, basically, I want to, steal some code. I have remote access. Let's say there's no shared resources because there's no multi-tenancy yet, but maybe I can, measure some timing of the circuit execution, for example. So you basically kind of can pick a path through all of these to identify different types of possible attacks. Um, so the side channels in general are passive, but they can interact with fault injection. So it's kind of nice, some also interesting relationship between side channels and fault injection. Basically, uh, in one way, fault injection can actually create some side channels. A classical example of fault injection creating a side channels is a fault would kind of somehow cause the system to output some errors information, and then comparing the faulty and non-faulty output, you can leverage that to learn something. On the other hand, side channels can sort of try to with the side channels, you can monitor how the system is executing, so they can tell you when to inject the fault. So, like for the fault injection, you always have to pick some time when you're injecting the fault. But like, how do you know what the good time is? Like, for example, I want to inject some fault, 10 cycles after a circuit has started, but how do I know the circuit has started? So you can use a side channel to figure out what's happening, and then use that to trigger a fault injection. And then there's very, I don't know, maybe this is tangential, but there's last few years, there's a very interesting thing about statistical ineffective fault analysis. So this actually combines, again, you use a fault injection to get some output, and that becomes a side channel. But really cool thing about this is that for the statistical ineffective fault analysis, basically you inject a fault, and then you observe when that doesn't create a problem at the output. So you can imagine here just like a very dummy example. Let's say the fault would cause some register to switch to 0. Now, but if that register was already 0, then the fault does nothing to the 0, changes to a 0, and then there's no change in the output. So the cool thing is, you actually learn. So by injecting the fault and then observing that there's no change in output, you learn in this case that register was already 0. So this is kind of like I don't know, maybe somewhat backwards thinking about it, but it can be very useful, where you inject faults at different places, and let's say when you don't observe a error in the output, you learn something about the intermediate data if you know the effect of the fault. So this is sort of a very, very clever trick. And then also if you have this, like if you do fault injection, usually, your system messes up or gives you the wrong output, which means that it's easy to observe. If you have these ineffective faults, you inject a fault, there's no change in output, so nobody knows anything was going on. So it's a little bit more stealthy than other types of attacks. So anyway, maybe a side, but kind of an interesting thing that the faults can be combined with side channels, but they don't always have to give you wrong results. They can give you actually correct results, and you learn some information from that. And then, oh yeah, I also wanted to mention the interaction of the attacker with the system. So how do you actually, how does the attacker, do they change anything or not? So in general, we have either passive attackers, like for side channels, we're just collecting some information. So basically, you're not changing anything. Or you have active attackers where you're changing something like a fault injection, where you're inducing some change into the system. There is sort of a maybe there is sort of like a passive, so you have passive non-invasive where you collect. Um, um, uh, so you have fully passive where you really do nothing. So for example, if you just stand away from the system and you measure the EM radiation from that system, it's really, you're not doing anything. For a lot of things, for the side channels, it is passive because you're not modifying the system, but it sort of requires, like for power side channels, you do have to connect something to the system to measure the power. So it's kind of, it's not exactly fully passive because you did have to change something, but that change is maybe just connecting like a probe, or you're collecting the timing information by running some code on the system. So you still have to load some code and run on the system. So you could be like really fully passive where you have nothing to do with the system, you just observe it. But in most cases, for the side channel, you're not changing the operation of the system, but you still have to, load some code or maybe touch the machine to collect the information. Yeah. And then again, passive active attacks are also orthogonal to the supply chain attack. So again, if you have a supply chain attack, that is sort of like an active attack where you modify something, but you modified it at the manufacturing time or when the code was being, or hardware being distributed. So somehow supply chain is always orthogonal to all of these different categories. And then when the attacker actually gets that information, there are many different ways of analyzing the data. We're not going to cover these, but sort of it ranges from like a simple SPAs, like simple power analysis, for example, so where you can look at the power a single trace, where you look at the power consumption, and then maybe you can deduce some information directly from the trace. So single trace attacks are somehow most desirable because you collect one trace of information like power changes and you decode some information from that. But usually there's a lot of noise and it's not as easy that you can just look at the trace to see what's happening. So you have like differential and correlation analysis attacks where you collect many samples and then from that you can recover the information sort of statistically. Template attacks are things where actually you have access to the system to sort of create these templates, or you know how systems should behave under certain conditions, and then when you collect the traces, you match which template does it match, and of course now people are using machine learning to just dump all the data that's collected and then try to use machine learning to extract some information from it. For machine learning or for these other differential or correlation analysis attacks, you do need a lot of observations. So, if the quantum circuit only executes once, it would be really hard to get more than one observation. So, ideally we could have like a simple attacks where you just collect a single trace, but in practice you need to collect many traces, which maybe makes some of the side channels less practical because yes, it does work, but you need to run the the victim program or the victim circuit many times, and in practice, people don't do that. They run the circuit once and they're done. Okay, so putting this together, I hope this kind of summarizes the different side channels, different side channel threads. So you have the different, the type, the source, the amount of sharing, the access, and then what's the eventual target. And then somehow orthogonal to this, we have supply chain attacks, and then given all of this, there are different data analysis techniques to given the timing information, how do I recover something about the code or data? And then also somehow we have different type amounts of interaction. So how much interaction do I have with the system, passive or active, to collect that information? So I don't know, maybe not the best figure, but I hope it kind of captures the different kind of categories and things that we consider in side chains. Yeah. Any questions about this part? Yeah, question.
Have a correlation analysis and template attacks. Can you just re-explain that if you could?
Okay, yeah. So for the differential power analysis, basically you collect many traces, and then you make assumptions about, is the secret bit 1 or 0, and then you sort of statistically compare different traces. In the correlation analysis, you have some model. So in the differential analysis, you don't have like a model of, let's say, how the power consumption corresponds to the instructions. You're just collecting many samples and you're comparing them. In the correlation analysis, you do have some models. So I know, okay, this is how, usually we use like what's called a Hamming weight model. So basically, the more bits that flip in a register would result in higher power consumption. So you have some model of the power consumption, and what you're trying to match what you observe to that model. And the sort of Hamming weight models, at least for classical computers, pretty standard, and so people use it quite often. So you have so if you know for power or another thing, if you know how the power or EM corresponds to the instructions, you can use the correlation analysis, and then you should be able to use fewer samples than the differential analysis. And then the template attack. I guess it's similar to the correlation analysis, but the correlation analysis is like you have like a theoretical model, like for the Hamming weight model, number of bit flips that flip correspond to the power. For the template attack, maybe there's not a theoretical model, but you made some observations, like you actually run different instructions on this computer, and then you see what's the power profile, and then that becomes something that you match. That's the template that you're matching against. Yeah, so
just to share one something, the differential is you just take a bunch of traces and then you're kind of comparing traces without necessarily a model. Correlation is you have some theoretical model you're mapping against, and then template is you're creating a model based off of this specific data.
or you build for the template, you build a model, let's say, of a specific device, or you build it. Yeah, so it's like you sort of like almost like fingerprinting. How much EM does this device generate for different instructions? Yeah.
For the template attacks, how reliable is that? Is there a way like I could run an all-in-one device and profile it with like high probability that I know based on these previous traces that this is what's running?
Right. Good question. So how reliable all of this is. So I think that the biggest problem is that in all the side channels, especially for like power or EM, you're taking a measurement, and that measurement can be very noisy. So like on a computer, let's say I'm doing encryption, but in the background there's an operating system running. You're sending network packets. There's a whole bunch of power consumption or EM that's generated that's unrelated to the actually your target. So all of these. So for the template attacks, I think especially if you build a template, let's say of a device, but then when you're actually doing the attack, I don't know, there's some new activity that would change that. Let's say you build a template when the computer is sort of idle and just running encryption. And then when you collect the power traces, when the computer is, I don't know, you're watching movies and there's a bunch of network traffic, the power profile would maybe change and it's harder to match. So it's very sensitive to noise for all of them in general. But research versus practice. So in research, if you really turn everything off and you just have one algorithm running and you measure the power, these work very well. Like in practice, if this is a cloud server in a data center, bunch of interference, this might not work well at all. So I think this is sort of maybe where people are looking more towards machine learning, where if there's a lot of external noise, maybe that can help filter things out. But if the noise, let's say, if the noise is pretty limited, then things like the correlation analysis with the Hamming weight model works very well. It's very established and it's very accurate. So really the problem is how much noise there is in the measurement. And let's say the academic experiments have little noise to demonstrate something. When you put it in an actual device, they might have much more noise and it doesn't work anymore.
That's pretty interesting.
Yeah. So I think the for all the anyways, maybe separate discussion, but for all the side channel attacks, I mean, they work very well in isolation, but on a real system, oftentimes that's a big question in can I get these high bandwidths when there's so many other things happening on the system? That's a big challenge, and maybe sometimes makes things less practical. But on the flip side, like at least for example for quantum computers, since right now there's no multi-tenancy, you don't have that many users, maybe the system is simpler. Maybe that means that the attacks are actually more realistic because the whole thing is somehow, less users, less noise, less things are happening. So, I don't know. We're trying to find out. um, um, okay, yeah. So and then perfect, great question, thank you. And yes, I already showed this. So kind of maybe this summarizes the different side channels. Okay, so coming back a little bit more quicker, we have two more things I want to kind of talk about different different categories for thinking about fault injection and then the side channels on fault tolerant quantum computers. So sort of again, why fault injection attacks on fault tolerant quantum computers? This is the same motivation as for NISQ machine. The motivation really doesn't change. Maybe you want to change so the fault injection could let you change some inputs to affect the computation, maybe directly change the results of the computation to get wrong output, or in some sense maybe you can actually steer the computation to an attacker specific output to get the output that you want. And so the objective is really the same as for NISQ machines, but the system is a little bit different because now you have an error correcting algorithm and an error correcting code running on top of the qubits. But still, the fault would focus on the controller or the QPU. Just as very short detour into NISQ versus FTQC. So for NISQ, basically these are current machines with hundreds, maybe thousands of physical qubits, but you execute your gates directly on the qubits without any error correction. Maybe there's some error mitigation mechanisms, but you're really sort of running on the qubits. And then FTQC are the fault-tolerant quantum computers where you use many physical qubits to create one logical qubit. The ratio varies really on the error correction code and then the architecture, but it's sort of 100 to 1 plus or minus a little bit. But so it takes a lot of physical qubits to create one logical qubit, but the logical qubit is error corrected, so much less noisy. And just kind of for the NISQ, a lot of the security threats are due to the noise, due to the fact that there's no error correction, and then maybe you have lower level access because you can execute quantum gates directly, or you can maybe even control the pulse parameters of those gates. Now, for the FTQC, the focus might be more on the error correction itself and the decoder, because there's much less noise because everything is error corrected, and maybe you don't have low-level access to the control pulses. So really the focus is more on the error correction, and for both, it's more about either monitoring or changing the execution. But for side channels, which we'll talk about in the last part, you can't clone the qubits, whether they're logical or physical, but you can monitor the execution. You could change the execution through fault injection, change things in the controller to change the instructions that are executed. And this is we'll come back to error correction again in the future when we talk about the quantum computing concepts. But at the high level, in error correction, you have many physical qubits that are used to create a logical qubit, and typically they're divided into either data qubits that are storing the quantum states, and some auxiliary qubits that are basically used to measure and decide if a qubit has flipped. So you have this array of qubits, and on the hardware side, each physical qubit is connected to the controller, just like in a NISQ machine. That part doesn't change, but now each group of qubits is used to define one logical qubit that either stores the data or interacts with other logical qubits for computation. And then not surprisingly, for the fault injection, each of these parts can be a target of fault injection in FTQC. Either the controller, which now is expanded with a decoder for decoding logical qubits. You could still inject faults in the physical qubits, or try to inject faults in the logical qubits. So these are kind of the three layers for the fault injection. So here I tried to come up with a categorization for the fault target, model, bound, and lifespan, similar to that we have for NISQ, but for FTQC, where basically the main thing is some of the targets change, maybe some of the lifespans change as well, as we will see. So this is sort of a pretty fresh categorization. So hopefully it covers everything. But basically, in terms of the targets, we still have the QPU and the controller. The added part is that on top of the controller, there's a decoder, either in hardware or in software, usually running on the controller, that does the error correction. So the controller basically talks to the physical qubits, and then the decoder runs on top of that and decides, builds the logical qubits and decides what to error correct. And like in NISQ, there still might be some coprocessor or GPU that's being used, but I'm leaving those out for now. So within those components, the target could be some specific submodule of the component. So in QPU, you still can target the physical qubits or the coupling. So you can have some fault in the QPU. In some sense, the QPU doesn't know you're running logical qubits. It's just executing physical qubits that are being executed, and error corrected or not, that doesn't in some sense change. But what changes is that if you inject some fault in a physical qubit, maybe the error correction algorithm takes care of it at the higher level. So but at the QPU, it's still the physical qubits or the couplings. Now in the quantum computer controller, I try to divide it up into sort of the more clearly into the analog part and the digital part. So at the end of the day, the quantum computer controller takes some instructions and sends out analog signals to the qubits, or reads the reflected signals to get the data out of the qubit. So for the analog part, you have the analog part of the digital to analog converter or analog to digital converter, and then I also put in the the actual cables or the way you send the signals to the qubits. These are sort of analog signals. So your fault could target the DAC or the ADC, or it could target the cable that's going between the DAC and the quantum computer. And this is all in the analog domain. Now in the controller, you also have the digital domain where all the pulses are specified as just ones and zeros that define the amplitude, the phase, whatever the envelope of the analog signals. So the digital specification includes things like the controller has some registers where it stores the digital data. It has some memory, DRAM, SRAM, maybe other types of memory where it stores information about the control pulses. The controller also, of course, is doing some digital computation to determine, which pulse to send or when to send it. So you could target, if you mess up the registers of the controller, you could mess up the pulse that is being sent, or if you mess up the computation that's being done by the controller, maybe it skips and some quantum gates are not executed. And then also you have the DAC has a digital input. So the input to the DAC is like 16 or 32 bits that specifies the amplitude at each instance. So if you're able to modify or fault the digital input to the DAC or the digital output of the ADC, that kind of messes up the operation. So really the target can be in the digital domain where you're sort of flipping the bits, or in the analog domain where you're messing up with the signals. And the decoder sort of is on top of the controller, but it's purely digital. So the decoder just gets digital information about the state of the qubits and then everything digitally. So the decoder, you would have just regular, attacks that flip bits in memory or registers or during computation. So the fault models are actually I think pretty much identical to what we talked about in NISQ, that for qubits the faults could be either unitary or non-unitary operations. I guess maybe enable disable comes under non-unitary operations. And then I tried to color code it a little bit, that for the analog part, the fault model would be more about something, change the amplitude or phase or shape of the pulse, which would really affect either the DACs or the cables. Maybe you could attenuate the signal while it's going through the cable. And then for the digital fault, it can be either stack at 0 or 1 or toggle bits. Basically, you're flipping bits or you're forcing certain digital bits to be stuck. I think I think you can make an assumption that if you fault the processor, like let's say if you fault the processor and it does some computation incorrectly, then that would result in some data bits being sort of incorrect, which kind of becomes like you're toggling the bit. So some faults in the computation would end up showing up as just bits being flipped in somewhere in some register or some memory. So I think this is the fault models are basically the same as NISQ, maybe just clarifying a little bit better where the targets are. And then really the decoder is quite important, but it's purely digital. And then the fault bound is also the same, just single fault or multi-fault. Now for the fault lifespan, things I think here change a little bit. So for the error correction code, there's sort of like an error correction cycle where you read all the physical qubits, you decode the data, you figure out if there's an error, and then you apply the correction, and then sort of one cycle is called an error correction cycle. So when you have a fault, you could target maybe just one physical gate or one physical qubit. That would be just sort of one gate, just as in NISQ, you just target one gate. Or the fault could maybe target one error correction cycle. So especially if you target the controller or the decoder, maybe you're faulting one full error correction cycle. And then as the program executes, it's there's many error correction cycles that are running. So maybe you could fault multiple error correction cycles. So those are sort of the new kind of granularities of the lifespans. I think especially if you target the QPU, it will be really more about one physical gate or maybe multiple physical gates. But if you target the controller, it'll be more like, one per error correction cycle or something for many error correction cycles. And then the other lifespans I think are sort of stay the same. Like, so, the execution, you could cause fault that affects the whole execution of a error corrected circuit. So like a single job or again, multiple jobs, there's still calibration going on. So fault that lasts for many jobs, many users between the calibration cycles. Again, something that, some faults, maybe there's a way to mess up the qubits, that the only way to do it is to actually, warm up the fridge and then reset the qubits, or in some uh, neutral atom or trapped ion architectures, maybe, you have to sort of bring in new atoms, so sort of power cycle, or, if you destroy the machine, it's forever. So if you burn something, that could be, a fault that lasts forever. And then similar to NISQ, the longer the lifespan, the easier it's to observe. If there's a fault, like if there's a fault in single physical gate or single error correction cycle, it might be hard to observe, or if you even notice it, it might be hard to attribute the fault to an attacker. If it's like forever, then clearly the machine is broken and it's easy to find. So yeah, so I think these are the categories, and they don't change much from NISQ, except maybe different lifespans, and then I mean, not different targets, but now you can target the digital signals, digital specification in the controller or in the decoder. So yeah, are there any questions about this? I tried to make them similar to the NISQ to easier to understand. Okay, so maybe I thought to add this. I don't know if it fits very well, but so when we talk about fault injection, at least in NISQ, we consider a lot about crosstalk between different gates. Now, so there's some when you have an FTQC, now you have some challenges to crosstalk. So I think the main question currently is, can there be crosstalk between logical qubits, or how you would execute or create crosstalk between logical qubits? And so I think that the main challenge is that there is crosstalk between physical qubits, but if you're using an FTQC computer, each user has an access to a logical qubit. So then if the only thing they can do is work with a logical qubit, they can no longer specify custom control pulses that might create a lot of noise. So, if the user has access to logical qubits and cannot specify the physical gates or pulses, is really crosstalk possible? And so on one hand, with error correction, it should be harder to create crosstalk because these patches are error corrected and the user has limited access. But some open questions are, is there some way to abuse the error correction code to sort of actually create a lot of noise? I'm not sure that such a thing exists, but maybe can the user somehow escape from the logical abstraction? Like on a classical computer, you're running as a user, and then maybe there's a privilege escalation and you become the root user or the administrator. Can you somehow escape from this logical qubit abstraction? We don't know. Or another one, can the user force another user to downgrade their error correction code? So we haven't talked much about error correction code, but you can have different sizes of error correction codes depending on the amount of errors you have in your system. And if the cloud provider allows you to choose the error correction code, maybe somehow you can end up in a worse one than you need. I think in classical computers, there's a sort of, at least in computer networking, there's sort of like there's a downgrading attack where your computer talks to a server, but the server on purpose says, the only encryption I support is this very old algorithm. And then kind of this forces your computer to downgrade to a very old encryption algorithm because that's what the server advertises, like a downgrade attack where you're forced into a very, like, if you don't specify like the minimum level of encryption, a malicious server might force you into a lower level encryption by saying this is the only thing I support. So again, if somehow a user is forced to use a smaller error correction code, then the patches will be more susceptible to noise, and you might have some crosstalk. So I thought kind of interesting and useful to keep in mind that in NISQ, crosstalk is really, I don't say popular, but it's a lot of crosstalk attacks have been shown. Now the question is how this works out in FTQC. On one hand, it should be less possible because you have error correction, because you have logical patches, because you have less access. But on the other hand, FTQC is not really deployed in practice. So are there some issues like this? So something to consider about the crosstalk, and then maybe one reason we didn't really have like a crosstalk related project for this class this year is that conceptually it becomes harder to justify crosstalk attacks if you have error correction running on top of the qubits. Okay, all right. So only very few slides about the last category. So we covered the fault injection and side channels in NISQ, fault injection FTQC. So then the side channels in FTQC, and not to repeat all the components of the quantum computer again, just kind of wanted to really again summarize why do we want a side channel. So a side channel in sorry, this should say FTQC. So side channel attacks on FTQC, the motivation is again similar. Can you leak some inputs or the outputs? Can you leak the instructions that you're executing? Can you leak some things about the timing? So it's the same as NISQ, but now you have the decoder running on the controller, the error correction running on top of the controller, so the components change. And the picture stays the same. So you can have the leaks either at the controller, leaks from operation of the physical qubits, or maybe some leaks from operation of the logical qubit. So this is where the side channels in FTQC can come. Okay, unsurprising. And then this is the same figure as for NISQ, where basically you have the same types of leaks, sources, sharing, things like that. I think really the main thing that expands is the surface, where these leaks might come not just from the controller, but from the error correction code decoder, from the decoder that's running on top of the controller. So you can think of it that sort of in fault-tolerant quantum computers, there's one more, or the number of sources increases because now you have decoder in addition to the controller, but other things should not change. Maybe because you have error correction, multi-tenancy and sharing among users would be more feasible. So maybe the amount of sharing will be increased in FTQC. On the other hand, FTQC requires many physical qubits per logical qubit, so maybe there's not enough resources to do any sharing after all. So I think that this, I didn't want to repeat the NISQ part. So this is basically the same thing as for NISQ, but the sources become a little bit bigger. Okay, so I think that's it for today. So hopefully kind of covered the side channels in NISQ, in addition to the fault injection we talked about before, and we talked about fault injection and side channels in FTQC. So next time we'll transition, talk more about quantum computing concepts. So we'll have maybe two lectures about quantum computing concepts, and then we'll go back to talk about sort of lessons we learned from classical computer security, hardware security, and how these kind of can drive what we think about quantum computer security. Okay, all right. So thanks so much, and okay, stop recording.